So this video we're going to review section 2, which is carboxylic acids and beyond. And what we're going to do is we'll first of all take a quick overview of how these four particular families that we're focusing on are interrelated. And this is just one of the sections from your poster. So when I draw the links between all four in this manner, then I'll individually look at each of the families and talk about their formation, the particular reactions they undergo, and any tests that you use to identify or distinguish them experimentally. So with carboxylic acids and the links with these other families, like we always do with these schemes, is we identify the functional groups first of all. So we're starting off with carboxylic acids. And remember, our carboxylic acid would have come from the complete oxidation of a primary alcohol, and then you end up with the carboxylic acid functional group. Acyl chlorides, the functional group is a double bonded carbon to a chlorine. Esters, it's a double bonded carbon, then a single bond to an oxygen, then the other rest of the molecule. So that's the ester functional group. And then the amide functional group is a double bonded carbon and then NH2. And you can clearly see, hopefully, the common part of the molecule, or the part of the molecule that is in common with all of these, is the C double bond O, which is referred to as the carbonyl group. So if we just take a look at how you get from carboxylic acids to acyl chlorides, first of all, like the main group which is different is the fact that the carboxylic acid has the OH group there, whereas an acyl chloride has the chlorine. So what we have here is nucleophilic substitution. Chlorine for an OH and this is nucleophilic substitution. So we performed that, or we demonstrated that in the lab for you guys. Then to get the reverse process, to get from acyl chlorides back to carboxylic acids, we introduced a sixth type of reaction known as hydrolysis. So we use water, just pure water, so this is neutral hydrolysis. And we'll discuss that when we do our specific section on acyl chlorides, where the hydrolysis is the sixth reaction type. The other five being condensation, elimination, addition, substitution, and redox reactions. So that's the link between carboxylic acids and acyl chlorides. So the next thing we want to look at will be each of these families individually. So what I'm going to do now is just create a new tab, and we'll talk about acyl chlorides. So family 1, acyl chlorides. Okay, so the first thing we'll look at is their formation. So formation of acyl chlorides. We're talking about nucleophilic substitution on a carboxylic acid. Nucleophilic substitution on a carboxylic acid using PCl3, phosphorus trichloride, PCl5, phosphorus pentachloride, or SOCl2, which is thionyl chloride. The next thing is to look at the four reactions of acyl chlorides. So I like to teach it this way, so then if you guys have memorized that there are four possible reactions of acyl chlorides, then you can start to identify them in an exam question. And the acronym I've used here is WA, or WA, like a baby crying. So on your poster you have a little picture of a baby. Roughly the picture looks like that, so a little bit funny, but it's supposed to be a baby crying. And each of the letters W and the AAA stand for one of the four reactions of an acyl chloride. So acyl chlorides can react with water, which is your hydrolysis back to a carboxylic acid. Acyl chlorides can react with an alcohol, which forms an ester. Acyl chlorides can react with ammonia, which will form an amide, or alternatively, you can use a primary or secondary amine, and that will form a secondary and tertiary amide, respectively. So we'll talk about these reactions individually in a second. Just a general note here, and this is why I had to perform each of these reactions as a demonstration. All reactions of acyl chlorides are vigorous. I mean, we took one chemical, and as soon as you added the reactant to the acyl chloride, there was quite a vigorous splutter or eruption almost as the two chemicals were mixed. Definitely not something that you want to catch in your eye. But all reactions are vigorous, and they produce hydrogen chloride gas, which again is very bad for your eyes. So definitely safety glasses needed, performed in a fume hood, and only as a demonstration. So just to talk about each of these reactions individually, so we've just introduced 4 reactions, and we want to add these to our flow chart from before. So if we go back now, so reaction number 1 with water we have here, which is hydrolysis. Now, hydrolysis, if I just go back here for a second, with water, this reaction is hydrolysis. And hydrolysis is a compound word made up of hydro, which refers to water, and lysis, which means to split. So it's the splitting of a compound using water. And you can have acid, basic, or neutral hydrolysis, depending on the product that you desire. And these are 3 types of hydrolysis you guys need to know for level 3 organic chemistry. So back in our flow chart, we have the first type of reaction, which is neutral hydrolysis, and that takes an acyl chloride back to a carboxylic acid. Then you can have an acyl chloride plus an alcohol, can make an ester. Because all reactions of acyl chlorides are quite vigorous, this is the faster way to produce an ester. You can produce an ester from a carboxylic acid, but that reaction is very slow and is also reversible. So there's pros and cons. It's safer to do it from a carboxylic acid to an ester, but it's slow, whereas it's faster to do it from an acyl chloride to an ester, but it's more dangerous. So you weigh up your options there. But that's the second type of reaction in acyl chlorides. The third type of reaction is to add ammonia. We want this ammonia to be dissolved in an alcoholic solvent because we don't want the reverse scenario or reverse substitution happening where you would reform some of the carboxylic acid. So this is a substitution reaction. The other third type of reaction, so that's number 3, the fourth type of reaction rather on acyl chlorides, is to use a primary or secondary amine. So primary or secondary amine will also form an amide. So there are your 4 reactions in acyl chlorides. And we actually performed each one of those as demonstrations during class. The last thing to talk about here for acyl chlorides would be the tests to identify them. The ammonia test is quite a common one. So what you do here is you just need to simply have concentrated ammonia. So this is concentrated NH3. It will vaporize quite easily, and the vapor from concentrated ammonia, if that mixes with the vapor coming off, so the HCl vapor coming off any acyl chloride reaction, then those 2 vapors will interact according to this equation. So you'll have ammonia vapor plus hydrogen chloride vapor, and the products will be NH4 plus and then Cl minus, and they'll complex together to form cloudy white smoke. So that ammonium chloride smoke is a test for acyl chlorides. The other thing you can do for acyl chlorides is obviously they're producing an acidic gas. So that acidic gas would turn blue litmus red. So there's your blue litmus, and the acidic HCl gas would turn your blue litmus red. So we just signify that with some red color here. So that would be the second major test for acyl chlorides. And apart from the fact that they also react vigorously with water. So that's everything you really need to know for acyl chlorides. The next thing to talk about, if we go back to our flow chart, so we've done acyl chlorides. We now looked at esters later in the week. So we set up a new page for esters. Okay, so family number 2 we looked at this week were the esters. If we go back to our flow chart, esters, how are they formed? Well, it's a reversible reaction, like I say. So on my original poster, I really should have had reversible arrows. You use an alcohol, and because this reaction is so slow, you also need to help it out with sulfuric acid, which acts as a catalyst, and also as a dehydrating agent. Because you lose H2O in the process, and we'll take a look at that now in detail. So esters, so formation, formed either one by reacting an alcohol plus a carboxylic acid, which is slow and requires H2SO4 catalyst, or the second way is to add an alcohol to an acyl chloride, which is fast and no catalysis needed. So we're looking here at the first situation. So if I just take an example, so if we write down ethanoic acid, CH3COOH, plus methanol, this is going to be a slow reversible reaction requiring sulfuric acid, H2SO4, requiring sulfuric acid, and you also get the loss of water. So the end product is going to be CH3, C double bond O bonded to oxygen, and I'll just use a different color to highlight the alcohol addition. CH3 there, plus your H2O. And your H2O comes from there and from there. So this product, in naming it, the carboxylic acid was ethanoic acid. The alcohol used was methanol. So as I tell students when you're naming esters, just draw a line down past the end of the functional group. So draw a line down, a line of division, and the main ester part becomes the anoate bit, and that always comes from the carboxylic acid. So this is going to be ethanoate. And then this part here, which comes to the right-hand side of the demarcation line, is the side group, which is going to be from the alcohol. So this is methyl ethanoate plus water. So that's your reaction for the formation of an ester using an alcohol and a carboxylic acid. As I said, the reaction is slow, it's reversible, and to speed things up a bit, the sulfuric acid acts to dehydrate the water byproduct. That helps to speed up the reaction. Okay, so that's the formation of esters. The second thing we looked at were any reactions of esters. Now, reactions of esters, so the reactions of esters, for level 3, there's no real reactions that you guys need to know. If you reverse back to the poster, esters can be used to form things called triesters, and I'll just briefly talk about them here. So triesters have 3 ester groups in them. I need to draw this properly, so hang on and just delete that for a second. So a better way to represent triesters would be a long fatty acid chain. And then you have your ester group there, that's one of them. Then a second chain, second ester group, and then a third one, and that's what your triester is. And these can complex with triglycerol to produce triglycerides, and this is used in soap making. So that's a separate lesson that I'll do when we come back after the holidays. But that's the main thing you guys need to know about what esters are useful for. If we go back to our particular page here, just with esters, now tests for esters, so that's really kind of the page with the introduction. So see separate video. Okay, so tests for esters or identifying esters. Okay, so esters have quite low boiling points because they're incapable of hydrogen bonding. So no hydrogen bonding. So as a result, esters will vaporize very easily at room temperature and pressure, so they have quite pungent smells. The short chain ones, short chain esters like ethyl ethanoate or methyl ethanoate, smell like glue, and then the long chain ones smell sweet, like synthetic fruit smells. And that's all we really covered on esters. One other thing I could mention about esters is because they're not very polar, so don't mix with water. And this is why one of the steps in your experiment was to, after you performed your carboxylic acid plus your alcohol reaction, you were told to add some water. And the idea here was the water would act to separate out the ester product from any unreacted carboxylic acid and alcohol, which are both miscible with water. So if I just represent this with a diagram, this is water. Water is a polar solvent. And inside the water, you would have any unreacted carboxylic acid, and you would have any unreacted alcohol. In the top layer, then, you would separate out your ester. So you'd have a top layer of ester. Just lost my diagram there. So top layer of ester, which is immiscible with water. So this is your ester product. And that's immiscible because it's non-polar. And this is a nice simple way to separate out your ester, and you should therefore get a better smell of your ester product. Because otherwise the carboxylic acid product or reactant is too overbearing. So that was just one other little thing, one of the physical property of esters. Okay, so the final group then to look at were amides. And we've already talked about the formation of amides from acyl chlorides using a primary or secondary amine or using ammonia. What we want to talk about now is the formation of amides briefly from carboxylic acid. So this is something I missed out in lessons during the week. So how do you get from carboxylic acids to amides, and then how do you get back from amides to carboxylic acids? And also, so this here is acidic hydrolysis, but you can also have alkaline hydrolysis as well of amides, so we need to talk about that too. So a separate one last tab for amides, number 3, the third family. So again, same format, we'll talk about formation, then we'll talk about any other relevant reactions, and then how do you identify amides. So there are 3 main ways that amides can be formed. We had an acyl chloride reacting with ammonia, so let's look at that first. So if we have ethanol chloride plus ammonia, alcoholic, we will form the amide ethanamide. So that's ethanamide right there, plus with all reactions of acyl chlorides you get HCl. So that's ethanamide. This would be nucleophilic substitution in this case, because you have one straight nucleophile for another. So this is nucleophilic substitution. The next situation we can have is an acyl chloride plus a primary or secondary amine. So the same acyl chloride, ethanoyl chloride. In this case, we have aminomethane or methanamine, aka methanamine, so CH3NH2. In this case, we have the product CH3. We'll just use a different color then for the addition of the amine, which is always via the nitrogen atom. And then you have CH3 stuck on there plus HCl. So this is actually could be referred to as a condensation reaction, because you have two relatively large molecules joining together with the removal of a smaller molecule, in this case HCl. So that would be a condensation reaction. This here is called N-methyl, because there's a methyl group stuck onto the nitrogen, and then ethanamide, N-methyl ethanamide, and this is a secondary amide, because there are two carbons attached to the central nitrogen. So that's how you name secondary amides. And the third way, which is not referred to quite often on exam papers, but I did find a question on it in one of the exam years, was formation from a carboxylic acid. So from a carboxylic acid, so we'll use ethanoic acid. You can react it with an amine as well. So we'll use methylamine again, or aminomethane. And then the products of that will be still a condensation reaction, but instead of HCl being eliminated, it's H2O in this case. So we'll just use different colors to signify the addition of the amine in this case to the carboxylic acid. CH3 plus H2O. So this is also a condensation reaction. Addition of two large molecules together with the loss of a smaller one. So they're the three main ways for forming amides. The second thing we looked at were acid and alkaline hydrolysis. So reactions of amides to know. Reactions of amides to know, basically you have acidic hydrolysis in acidic conditions. That was the first type of hydrolysis, and then the second type of hydrolysis was under alkaline conditions. We're just going to look at two equations. Remember, we discussed hydrolysis already and said that it is the splitting of a large molecule with water, and it can be performed under neutral, acidic, or alkaline conditions. Okay, so under acidic conditions, essentially what you do is you take an amide and return it to its carboxylic acid parent compound. So if we take ethanamide, CH3CONH2, and we add some water to it, there might be a small amount of hydrolysis would occur by itself, but we really need to add HCl to make that happen and force it to the carboxylic acid product. So if we do so, the products of this reaction will be ethanoic acid plus ammonium chloride. This acid product, a test that this has been successful, this acid product would turn blue litmus red. So that would be an effective test for the success of that reaction. So that is hydrolysis of an amide under acidic conditions. And then under alkaline conditions, to speed them up, we had you guys using the water bath. With alkaline conditions, you have the same amide, in this case ethanamide, plus sodium hydroxide, and the product of this reaction will be sodium ethanoate, which is odorless, but you also get ammonia gas. And we found that we had to really heat it to get this smell, and there's the characteristic smell of ammonia, and that would also turn red litmus blue. So you guys were using universal indicator solution, and we had a nice blue color for your alkaline condition, and we had a nice red color for your acidic condition. So that was quite a nice little demonstration of acid and base hydrolysis of amides. So that's everything you really need to know for amides. Amides just as well with tests. So synopsis of the tests for amides. Amides themselves are litmus neutral. So they don't turn red litmus blue like amines would. Amides had no real discernible odor. The ethanamide is solid at room temperature and pressure. Solid at room temperature and pressure. What else can we say? They're the main things with amides. Just check if I could say any more. Yeah, no reaction, so the litmus neutral, and that's all that you'd really be able to talk about in an exam paper. So the main thing, if they want to talk about amides in an exam paper, it has to be acid-base hydrolysis. So to go back to where we left off just for the holidays now. So with all of these families, we've talked about carboxylic acids, acyl, chlorides, esters, and amides. This little link here, as I say, from esters, to take esters over to triglycerides and saponification. We need to do a lesson on that when we come back. And then afterwards, it's a separate section on polymers, which I've also created a video of, and you guys can take a look at that in your own time as well.